Okay, so we're going to take a look at question 15.39A and D, and then 15.57A and B, and then we're going to tackle 15.59. So we'll start with 15.39, which just asks you about proton or NMR, carbon-13 NMR spectroscopy, how you would differentiate between the compounds. So if we think about, let's do carbon first, okay? So if we were doing carbon-13, okay, could anybody tell me for this first compound here how many signals you would see in the carbon-13, right? There's two axes of rotational symmetry here. So I got one, and then I got two, and then I got three, and then four. So you would see a total of four signals in the carbon-13 for this guy. So I'll put here four signals, okay? And then in the carbon-13 for this one here, I don't see any symmetry in here whatsoever. So I'll put here for this compound, no symmetry. And so every single carbon is going to be unique in this one. So we're going to get a total of 12 signals for this one. Now, what about proton? So I'll use red for my proton and I'll delete this, okay? So if I have my proton, so in terms of proton, you would only get two signals. Let me see here. So you'd get these ones and these ones are identical. And then these ones and these ones are identical. So for the proton, you would only see two signals. Let me use red. You'd see two signals for this one. But for the other one, if you look, this is unique, this is unique. It's 1, 2, 3, 4, 5, 6, 7, 8. So for the proton here, you would see a total of 8 signals because there's no symmetry in the compound whatsoever. All right, so if I look at D, so I'll do the carbon-13 for the compound on the left. Could anybody tell me how many carbon-13 signals you would see for this compound in the blue box? And it's not a trick question. How many signals would you see for that compound? So there'd be more than two, because don't forget the carbonyl carbon, right? The carbonyl counts as one. Remember, it's carbon-13. Yep, so you'd see three. Absolutely. So you'd see 1, 2, 3, right? So you'd see those three. Obviously, these two are identical, and then these two are identical. And so you get three signals. So we'll scribble that down. So three signals. What about the one on the right? Anybody figure out how many carbon-13 signals you'd have for that guy? And again, there's no trick or anything. Yep, thanks. Exactly. It's 5 signals. There's no symmetry, so 5 signals. And then for the proton, it's very similar in this case, right? For the proton, you have these two, and then you have these two. So you get a total of 2 signals for the compound on the left. And then for the compound on the right, well, everything is unique in there. So you'd get a total of 4 signals, right, for that one. Okay, so we figured that one out. I like question 15.57. I've actually asked this question on a quiz one time a few years ago. So they give you a formula and then they tell you something about the chemical shift. So remember that the little delta symbol, that represents the chemical shift in parts per million. So they give us C5H10O. So the first thing I notice is that we have an HDI equal to 1. And then we have a doublet that integrates for 6 protons at 1.09 parts per million. We have a singlet that integrates for 3 protons at 2.12. And then we have a septet that integrates for 1 proton at 2.58 parts per million. Does anybody recognize any of the 3 alkyl groups that we discussed? Ethyl, isopropyl, or tert-butyl in this one? Does anybody recognize any of those? Yeah, it looks like there's an isopropyl, right, Isaac? Yeah, so here I would say you have a doublet that integrates for, or sorry, a doublet that integrates for 6 protons, and then a septet that integrates for 1. So I would say isopropyl. So that means you've got this, right? You've got this piece, And then the only other signal you have is a singlet that integrates for 3. So that must be a methyl group, right? This has to be a CH3 group. If you tally up all the number of protons here, you have 3 plus 7, that gives you 10. So that means all you have is an isopropyl group and a methyl group. And then if you have an HDI of 1 and you're missing a carbon because there's a total of 5, here we only have 1, 2, 3, 4, right? So it has to be a carbonyl carbon. So the only possible way that we could put these together would be to have a carbonyl like this, and then to have a bond to the isopropyl. So we'll put the isopropyl over here. That didn't work very well, but let me do this. There we go. And then we put the methyl group on the other side like this, and we're done. So there you go. That must be the structure of the compound. It's the only possibility. Give me a thumbs up if you're with me on that, how I kind of put that together. Even if you're like 25% of the way, because you're going to have to try it yourself. Yeah, cool, cool. Okay, well, what was the other one I said was B? Okay, so let's give B the old college try. So in this one, we've got C5H12O. So our HDI is equal to 0. So that means if we have an oxygen, we've got either an alcohol or an ether. Those are the only two possibilities. Then we see we've got a triplet that integrates for 3 at 0.91, a singlet that integrates for 6 at 1.19, a quartet that integrates for 2 at 1.15, and a singlet that integrates for 1 at 2.24. Does anybody see any of the groups here, ethyl, isopropyl, or tert-butyl? And go with your gut. Does anybody see any of those 3 groups? Yeah, thanks, Arubio. Absolutely. I see an ethyl group in here too. So we have a triplet that integrates for 3 and a quartet that integrates for 2. So yes, we must have an ethyl group in here. So this would be our ethyl group like that. Okay, then what else do we have? We have 6 protons that give us a singlet. And then we have 1 proton that gives us a singlet. All right, so how are we going to put all this together? Well, we've got CH3, CH2, like that. And then if we have 6 protons that give us a singlet, and then we have 1 proton that gives us a singlet, we know that this is not an isopropyl, right? Because we'd see a doublet and a septet. So that means we have 1 proton that is not split. And so the only way we could do that is to have an alcohol. So this must be an alcohol. And then we have 6 protons that are not split by anything. And so the only way we could do that would be to have the alcohol like this, and then have the two methyl groups like this, okay? Because those are not going to be split. They're not going to split each other because they're equivalent. And they'd be too far apart anyway. They'd be 4 bond coupling. So this must be the compound. Would have to be this compound here. Anyhow, so what we'll do tomorrow is I want you to try this one for tomorrow and see if you can come up with a structure for that one. So the HDI, you just use the formula. So you remember the formula that we covered back in the infrared spectroscopy chapter? So it was HDI is equal to 1/2, 2 times the number of carbons plus 2 plus nitrogens subtract hydrogens, subtract halogens. That's how we calculate the HDI. All right. So let's do one more problem, 15.59. They gave us a proton NMR spectrum, and they gave us a carbon spectrum here. We've got 9 carbons in the compound, and it looks like we've got a total of how many signals? So we've got 1, 2, 3, 4, 5, 6, 7. So we've got 7 signals in the carbon. So that means there's symmetry somewhere in the compound. So there must be some kind of symmetry somewhere, because here we've only got 7 signals. And like I said, there's 9 carbons. Here we've got 4 signals in the proton. Did anybody calculate the HDI for the compound? HDI is equal to? Exactly, the HDI is equal to 5. Okay, what are some other low-hanging fruits that we could look for in here? Okay, if I have 5 protons, right? This represents 5 protons, 2 protons, 2 protons, and 1 proton. That's what those numbers represent above. 2 plus 2 plus 5 plus 1 gives me 10, and there are 10 protons in the molecule. But what region is this region here between 7 and 8 parts per million? What does that tell us? What kind of functional group do I have in the compound? If I have 5 protons in this region between 7 and 8, it's aromatic, exactly. So I've got an aromatic ring. Yep, there's no doubt about that. And if there's 5 protons, that means it's only attached to one thing. Rubiel or anybody, do you remember what this means? If I have 1 proton at like almost 12, you see it's very broad. You guys remember what functional group that must be? It's the highest of all the chemical shifts in proton. If you have to go back and look at the table, if you have to, that's why we're here. Could anybody tell me what functional group I'm looking at there? Could anybody tell me that functional group? Exactly. It's a carboxylic acid. Exactly. So there you go. So if I have a carboxylic acid, okay, and I have an aromatic ring, that takes care of all my HDI. So now I've got those 2 pieces, and it might be hard for you to see, but these 2 protons, this is a triplet and this is a triplet. So what does that mean? If you have 2 triplets that integrate for 2 protons, okay, we saw this earlier on today, 2 triplets that integrate for 2 protons each. It means that you've got CH2, CH2, but they're attached to 2 different things, right? So what's the only way you could put that together? Would be to have the aromatic ring, CH2, CH2, and then the carboxylic acid. So we don't even need the carbon to solve this problem, really. Okay. Now, in terms of the annotation for the proton NMR, we would start over here. We'd say A, B, C, D. So this would be the D protons. These would be the C protons. So C, 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 C. And then in terms of A and B, well, B would be more deshielded because it's next to the carbonyl, and A would be over here. But then in terms of our carbon NMR, if we label these A, B, C, D, E, F, G, like that, let's redraw the compound a second time, and let's see if the carbon 13 matches our structure. So we have something that looks like this. And so the carbon for the carbonyl must be this one. A and B would be the 2 methylenes, okay? The one that's going to have the higher chemical shift would probably be this one, and then A would be this one. And then we have the C, which is hard to see. We have C, D, E, and F, right? And we have 1, 2, 3, 4 types of carbons here. Well, you see that D and E are like twice the height. Okay, there's no integration in a carbon, but if it's double the height, it probably means there's double the carbons. So that would mean that these would be E and D. Okay, I'll put E and D on both of these. Now, as far as distinguishing them goes, I mean, the one that's more deshielded, E, would probably be the one that's attached to the substituent, okay, and the D would be the other one. But if you mix those up, I certainly wouldn't pick on you about it one bit. And then we have we have 2 other carbons. We have F and C. Well, the one that's more deshielded is probably the one that is attached, to the substituent, okay? And then C would probably be this one down here. So we could put E here and D here as well. There you go. So we were able to annotate both spectra. They line up with the structure that we propose, or at least the carbon does. So there you go. So what we're going to do tomorrow is we're going to solve this one, which uses IR and proton and carbon. And then we're also going to take a look at this one too. And let me just show you quickly here. So we're also going to take a look at, let me just give me 1 second here. Yeah, just give me 1 second and I'll project it here just so you know, especially if you're just watching the video. There, we're also going to take a look at these problems tomorrow. So this will be 06, 06, 18, 24. And there's some multiple choice questions in here about homotopic and antiotopic, diastereotopic. How many signals would you see? Downfield, upfield, that kind of stuff. Chemical shift practice. You can see there's a structure here about something about integration, two singlets, all good problems, good practice. Also another one here. Yeah, this is another good one. Okay, so there's a bunch of cool questions in here and we're going to try and take a look at all of these in class tomorrow. I mean, every single one. I even have one that has a depth 90 and a depth 135. So that's what we're going to work on tomorrow. Again, is we're going to finish the questions that we just looked at from Klein, and we're going to do all of these questions tomorrow. Okay, so make sure you take a look at them before class tomorrow. All right.